Okay, a very good evening to everyone. Okay, so today's question is I'm going to look at one of the most famous mathematical problem proposed, okay, by this Indian mathematician, Srinivasa Ramanujan. Okay, so for Mr. Ramanujan, okay, he proposed this question to the Journal of Mathematical Society of India, okay, in the early 1900s. So this problem is a problem in regards, okay, to nested radicals. So what is this question all about? Let's take a look. Okay, so I'm going to show everybody this problem. Now, this question is often seen in mathematical Olympia. It comes up very often. So this problem is, okay, asking us to solve this radical. Okay, it is the root of 1 plus 2, root of 1 plus 3, root of 1 plus 4, the root of 1 plus 5, and so on and so forth till infinity. What is this entire nested root? Oh, sorry, the entire nested radical equals to? Now, we all know, okay, we all know that it is equal to 3. If you do a research online, you can just find that it is 3. So not surprisingly, okay, under the comment section, everybody got the answer 3. Okay, everyone you can see here, okay, they got the answer 3. However, okay, this question, okay, someone actually commented that if you didn't memorize the answer beforehand, how would you solve it from scratch? Okay, he says that good question is not easy. Okay, he provided, okay, an assumption, a conjecture. All right, but okay, is there a way to prove, to generalize this entire thing algebraically and solve it more effectively? So I'm attempting this question, okay, and I hope that, okay, I'm able to solve it and provide some insight towards this famous mathematical problem. Okay, so coming back, okay, I'm going to share my screen one more time. Okay. Okay, and this is the problem. Okay, I write it down in my PowerPoint. I just put that 3 on the left-hand side and the entire nested radical on the right-hand side. So that's the problem. Yeah, but before I solve this problem, okay, there is actually a movie about Mr. Ramanujan, okay, about his trip towards England and meeting G.H. Hardy, okay, another mathematician. And if you have watched this movie, you can tell me whether is it a good movie or not. Me, myself, personally, I have not watched it on Netflix yet. Okay, so if you think that it's a good movie, just leave me a comment down below. All right. So speaking about that, okay, how am I going to show that? Okay, so basically, okay, if you look at the left-hand side, now coming back to the problem. Now the left-hand side, we know 3. 3 is the root of 9. Okay, that's very simple. Now 9 is 1 plus 8. So I root it. Okay, and 8 is 2 times 4. So it becomes 1 on one side. So 2 times 4 is 8. And you can see that 4 is the root of 16. Okay, now we have 2 over there now. So as this goes on, okay, 16 is 1 plus 15. And as you can see over here, now we have 15 is 3 times 5. Thus, if this is going on, 5 is the root of 25, you are actually able to identify that we can see that the entire thing is expanding out gradually into a nested radical. Okay, and we all know that all this is equal to 3. So if I go on and on, okay, you can see that I'm actually shifting out the 1. Okay, and you can see that over here you have a 2, a 2, a 3, a 4, and so on. So if this is going to go on and on, conjecturally, okay, if I'm going to base on conjecture, as this is going to tend towards infinity, this entire thing will converge to 3. Okay, but so far it's just a conjecture. How am I going to prove it? Okay, how am I? We actually saw this pattern. We see this pattern right now. But how am I going to justify it and find a general form algebraically? So in the following slides, I'm going to show you what I did. Okay, so now I'm going to show you the general proof of this problem. Now, very simple. I'm going to look at it as a very simple basic binomial expansion. Okay, I just use x and n. Okay, x and n squared is equals to x squared plus 2xn plus n squared. This one is very, very simple. So I don't have to go much how I derive that. Okay, now what happened is I'm actually factorizing x squared and 2nx. I'm factoring it out, okay, taking x as common factor, and the other one is x plus 2n. N squared, I remain as n squared. Okay, so now let's take a look what's happening next. Next, I'm very curious about x plus 2n. So x plus 2n, okay, if I'm going to look at x plus 2n, notice that, okay, before I look at x plus 2n, okay, I have to bring the square root over. Okay, if I square root on both sides, x plus n, okay, will be left on the left, and on the right, it will be the root, okay, the square root of n squared plus x times x plus 2n. Okay, I hope this part makes sense. So this is our very first radical. Now, if I want to continue, okay, if I look at x plus 2n now, x plus 2n squared, okay, as we can see that, okay, over here, if it's square, okay, you can have the same binomial one more time. Okay, as you can see over here, for xn, okay, for xn, I've just expressed it out as xn plus 3xn. For n squared is 3n squared plus n squared. Okay, for n squared. So I'm actually, okay, splitting the algebraical terms. Now, x squared, I just leave it as x squared. And notice, okay, what I did here was actually I'm just going to split out n squared. Okay, reason later I'll explain to you why I split out n squared. In this case, n and 3n squared will give you 4n squared. Okay, that one hang on. Now, what happened here? After which, from this point, these four terms, now I actually factorize them, okay, by grouping. I group out common terms, okay, and I obtain this expression over here. Okay, so I hope this part here is clear, because I'm just actually using x squared, 3xn, okay, and n xn and 3n squared. Okay, I just factor them out, okay, and there's a common factor x plus 3n. So without much to say, okay, so we have x plus n, okay, followed by x plus 3n plus n squared. I hope it makes sense so far. Okay, so the next step, like what I did just now, I'm taking square root on both sides, and thus I get this expression over here. So x plus 2n is the root of x plus n, x plus 3n plus n squared. At this point, I'm going to substitute this, okay, this equation here over here. Okay, so as you can see now, the roots, okay, the nested radicals are actually expanding. So I'm just going to substitute, and what I get, okay, if I'm going to substitute, now I'm getting, okay, the root of n squared plus x, okay, x is here, okay, and x plus 2n is the root of x plus n, x plus 3n plus n squared. Okay, so this is, okay, the procedure that I will be continuing. Okay, so the next step, okay, I'm very curious about x plus 3n. So x plus 3n squared, okay, same thing. I'm performing the exact same procedure as what I did just now for x plus 2n. So same thing, I expand it out. Okay, I group up the respective algebraical terms and factorize them out respectively by grouping method. So you can see what I just did over here. Okay, so it's exactly the same thing as what I did on top. Okay, and what I got for x plus 3n squared is x plus 2n, x plus 4n plus n squared. Okay, I hope it makes sense. So square, I bring over, becomes square root. So x plus 3n is the root of x plus 2n, x plus 4n plus n squared. Okay, so same thing, I obtain this whole expression. Notice, okay, when I actually factorize them out, when I actually factor them out, I'm actually taking by n squared. I'm trying to leave n squared alone, okay, to try to match, okay, the right-hand side of the main objective, the Ramanujan, okay, nested radicals. So n squared, later you will notice what happened. But for now, okay, as you can see, I'm actually taking out, what do I see here? Here is I'm using x squared and 4xn, okay, 2xn and 8n squared. Okay, so I factor it out, I get this expression here and this expression here. Okay, I hope it makes sense so far. So if I'm going to substitute x plus 3n, the radical form, into the expansion again, okay, what do I get? This is what I get. Okay, I get x plus n is the root of n squared plus x of the root of n squared plus x plus n of the root of x plus 2n, x plus 4n plus n squared. Okay, at this point, notice that, what do we notice? Now, for this, I will just actually put my n squared over here, but it doesn't matter because it's a plus, whichever order it doesn't matter. So we have an n squared plus, there's an n squared plus. Over here, okay, we also have an n squared plus. So what does this signify to us? N squared is repetitive, okay? If I just let it be certain value, it will turn into a constant. Okay, that's one thing. Now, what is interesting is, by looking at these two, okay, procedure, the same procedure that I performed repeatedly, what exactly happened is, now I have an x over here, okay, the x coefficient, okay, and the x plus n, okay, over here. Okay, and then the next term, let's take a look what happened after that. Now let's take a look at the next one. So now I'm going to put my equation over here. I put it back. Okay, I just put it here. So the next one is I want to look for x plus 4n. Okay, x plus 4n over here. So x plus 4n squared, same procedure, exactly the same, expanding, factorizing, grouping. Okay, these are very straightforward. So the expression for x plus 4n, okay, in radical form will be the root of x plus 3n, x plus 5n plus n squared. I hope it makes sense. Okay, so at this point, I'm same thing, what I did, exactly the same thing. I substitute it back into the nested radical, okay, for x plus 4n over here. So once I add it in, what happened? This whole thing will transform into the general form of the nested radical hierarchy of what Mr. Ramanujan is trying to achieve. So over here, x plus n, okay, if you notice something very interesting, okay, if you look at this, n squared is n squared, n squared, n squared, n squared. X plus n, x plus 2n. Now notice the 2n is out already. Okay, 2n, because we substitute x plus 4n here with this entire radical, we put it in. So this whole thing will be the root of x plus 3n. Okay, for me, I just put the n square over. It's the same thing. So the n square is this n square. Okay, x plus 3n, x plus 5n. So this whole thing, we actually notice a very interesting pattern. What is this pattern? Okay, x plus n, x plus 2n, x plus 3n. Notice, because next we are going to deal with x plus 5n. So notice we already have a pattern, x plus n, x plus 2n, x plus 3n. Next one, presume will be x plus 4n. Next one will be x plus 5n. Make sense? And so on. N square in every term, notice we will also have this n square inside the radical. So this whole thing, if I'm going to let it be certain value, don't you think it will be a constant? Okay, so this is the general algebraical form, okay, of, okay, the nested radical, okay, of x plus n. Why is this significant at this point? How is this going to help me to solve my problem? Okay, now let's take a look. I write this whole equation over. What happened? Remember I say I just have to substitute, let x and n be certain values. So if I let n be 1, x to be 2, notice x plus n is 1 plus 2. So when it is 1 and 2, if I add them up, what's going to happen is 3. Thus 3, okay, notice n is 1. So n square will be 1 because 1 square is 1. So 1 will be here. Okay, I hope it makes sense, because all of these terms, if I want to continue expanding into radical forms, n square will always be 1. So in other words, there will always be a 1 over here, 1 plus certain value, 1 plus certain value, 1 plus certain value. Okay, it makes sense, huh? So that's why over here I have 1, this is n square, 1, n square, another 1, and so on and so forth, 1 over here, another 1. So n square, we are settled. Now x is 2. This first x is 2. So this is 2. Okay. So what happened? The next term, okay, next term is x plus n. Okay, x plus n is 2 plus 1 is 3. So this is 3. Okay. So what's the next one? Next one is x plus 2n. 2n, okay, in this case is 2. X is 2. 2 plus 2 is 4. So we have a 4 here. Likewise, okay, if I'm going to continue x plus 3n, it gives you, okay, x plus 3n, okay, will be 3 plus 2 is 5. Yep. So you will have a 5 over here, and so on and so forth. Notice over here, the right hand side is the exact same thing, okay, as what the question that was proposed by Ramanujan. So Ramanujan actually proposed this question, and notice that on the left hand side is just simply 1 plus 2, 3. So this is how I prove, okay, this entire nested hierarchy, okay, of radicals via an algebraical proof, okay? And this is the general form that you should be expecting. Okay, so I hope that this question, and that's the answer, by the way. So I hope that this have created an interest. Once again, thank you very much for watching and have a nice day. Okay, good night. Bye.